All right, I'm Jalen, and then this is Asher,
Hello.
and this is our Moon 101 presentation. All right, so the first image that we have is the area around the Apollo 12 landing site, and you can see older craters and younger craters on top of the mare. Typically, younger craters are lighter around them, and they usually don't have more features on top of them, while you can see some of the older craters have smaller craters on top of them or begin to appear smoother and darker, and they soon blend in with the mare. And the light is coming from the left side on the bottom, and then this is kind of a description we have an outline of where they landed for the Apollo 12 missions over here. So they were in
I'm sorry, I'm going to interrupt you real quickly.
Of that, so that they could check in with that. And then you can
go ahead. So I'm having trouble hearing you. Breaking up a lot. And I think it's just a connection issue. It's a bandwidth thing. Go ahead and turn your camera off. We'll see if that may help.
Okay. Okay. Can you hear me better now?
I sure can. Yes.
Okay. Yeah. It was saying that the internet was bad. Where was I? Okay. Landing site. Okay. So yeah, I'm not sure if they plan to land exactly right there or somewhere nearby, but they got pretty close, so that was good.
All right, and image 2 is a picture of the elbow rail, which is a part of Hadley rail. This is a very image. The rail itself is probably one of the older features in the image. The mare surrounding it is definitely the oldest. Here. The light is coming in from the bottom with the kind of right angle on up, and this also takes the landing site, or not landing site, picture track that part of. You can't see in this image, but if you were to zoom in on like El Rock, you could see some certain tracks. There are a lot of older craters dotted around rail. You can tell they're aligned edges. And then on the next slide is a better image with a crater inside the rail itself. As you can see, it's much younger, it has more defined edges. The image in this slide is taken directly from El Rock. And as I stated before, if you zoomed in more, you could see the tracks from Apollo 15. I go back. The bottom of the image, there's a very bright white spot coming up towards the rail. That is debris from a crater that had impacted and is younger than the rail itself. As you see, the debris goes over into the rail. And the rail was most likely formed by volcanic lava flows that either cut through the surface themselves or were carving lava tubes, and those tubes then collapsed. And then this is again all just basically what I just talked about in text. And then image 3 here is all of the third image. It's Hadley Rail with Apennine Mountains to the east of it. This picture is flipped, so it would fit on the slide better, but cardinal directions, the Apennine Mountains down here are to the east, with Apollo 15 heading up the rail. We split up the image into 2 different sections. This is the first half. This depicts elbow rail was a large crater that cuts across the rail along with the Apennine Mountains that follow up along the east, and then most of the north. Hadley Rail and along with the Apennine Mountains are known as a large mark on the moon. The Mars obviously, again, with the mountains being younger because they probably formed with the moon during its formation. Apollo 15 is up near here, along with our call out pointed out, and a lot of tracks come down towards the mountains and towards this part of Elbow Rill with, as I said before, a younger crater with a more defined ridge cross-cutting across the rill.
And that was just our description in words of that image, as well as some facts. And then here is the bottom half, and you can see another young crater pictured at the bottom. This is a more blown out image, but you can see that the Apennine Mountains continue down on the right side of the Hadley Rill. The image before was more defined, but there's also like craters within the rill that you can't see in this, just because they've been smoothed over and they appear blended with the mare. As you see, you can see little ones here, but it looks like there might have been one here as well before that has been smoothed over time. And the light is coming, looks like it's coming directly from the right side. As you can see the shadowing on the left side of the mountains, and you can see the left side of the rill. And then here's kind of a description of that and some more facts. Yeah, and it just kind of shows the end of the rill, as well as some of the mountains ending. And then here is our sites. And that's the Moon 101 presentation.
Yeah, that's everything.
Next up is, would you like to do comments first on this one, or do you want them to go to Asteroid next?
Yeah, let's talk about this one first. Excuse me. Can you all hear me okay? Am I breaking up or anything?
Yeah, we can hear you all right.
Okay. So I apologize. I'm getting over bout of bronchitis, so I'm a little coughy. Can you go ahead and bring your slides back up?
Oh yeah, sorry.
So first, let's say great job. That was great. That was really good. I like how you marked up the image. You were pointing things out. I like how you had the image up and you were speaking to it. You weren't. You didn't have a bunch of words, basically.
Yeah.
Which is something we typically see a lot, of course, if you're not used to presenting, particularly material like this that you probably have never really seen until now. It can be intimidating to, or you might be more inclined to have a lot of text as a crutch, so to speak, on your slides, but you didn't. This is great. This is a great use of using text to help your presentation, instead of making your presentation all about text. Anyway, so yeah, these are all craters. Just a quick clarification question. The bottom pointer you have there pointing to Mare. Are you telling me that particular spot is Mare?
We're just saying that that's part of the mare, and it's just the general back area, I guess, behind the the craters and the other features. We didn't really think it was smart to outline that because it's kind of behind everything and that would be difficult, but we're not saying that specific spot is that now.
Okay, gotcha. That's kind of what I figured you were doing. I just wanted to clarify. No, you're absolutely right. This whole thing is a Mare. It's part of the Mare. In fact, and what you could do is not even have that tag, and just some point, early on where you start talking about these are craters all over, you can say this is, an image showing craters that are superimposed on Mare, something like that. That would get the point across that you're looking at entire Mare.
Yeah.
But to be honest, most people, especially scientists who are looking at this, are going to recognize that, especially given the scale that we're looking at here. They're gonna that would almost kind of be an unspoken thing you wouldn't have to say, but I'm glad you did for our purposes. And yes, that is the Apollo 12 site. And I don't know if you could tell from this image and the next one that you looked at that I actually inverted the image.
Yeah. When we were looking on LROC, I had to flip it around to see the exact image of that.
Yeah.
That
I
image. Yeah.
I did it on purpose. Number one, I wasn't sure. I chose that image because you can see the Apollo 12 site in it, but I didn't want to make it so obvious. So I
Yeah.
flipped it. Anyway, so you guys found that. That's cool. That or Miss Benzel told you. Either way, it is the Apollo. It is Apollo 12.
It was a little of both, because I'll tell you, I'd start on something and then I'd look over and they'd be, oh, I found this picture. I found this picture. Okay. So they just went for the pictures and finding them.
I
And
mean, it's good.
they were good at that. I didn't really have to do any coaching on that end.
Yeah, that's fine. Well, you got somebody who's interested in engineering and computers. You really can't pull up much over on them when it comes to online images. So go ahead and go back up again. I really didn't have much to say. I just want to see to make sure. Yeah, the lighting. So what was your, okay, so let me ask you this. I guess, some people, I would say about half and half. Half the teams, when they present this image, will say those are hills. And the other half say they're craters. And they are impact craters, as you said. Did you struggle with that? Or when you saw this, were you thinking those are impact craters?
So I was putting in the light arrow, and I thought it was coming in from the right side of the image, because those looked like hills at first glance to me. But taking it into LROC using the 3D globe version of the moon, you can kind of orient yourself so you see them dip into the surface as opposed to just a flat 2D image. So that's what basically confirmed that they were craters to me.
Yeah,
Okay.
as well as when we had this image, you can see
They look more like craters.
that they're craters in this image, because we were looking for the tracks from the Apollo 12 and where the Surveyor 3 was located.
Yeah, there's much more of a variety of crater sizes and things, and that helps. Okay, great. Yeah, you said something about the Apollo 12 landing site. So they pretty much did land where they wanted to. One of the engineering or technological goals, if you will, of the mission was to do a precision landing. Whereas with Apollo 11, they were just kind of like, well, we're going to land in this general area.
Like, let's hit the moon.
And then when they got there, they got close enough. There were little craters and things that the current maps we didn't know were there with the technology at the time. So Neil Armstrong did a great job of maneuvering to a place where they could set down. So in Apollo 12, yes, it was intended to land where it did because of the location of Surveyor 3. And they did go grab a piece of the spacecraft to bring back to Earth to run some analyses on that metal to see what being in space for 3 years does to break down that kind of stuff. Okay, anyway, so let's go on to the next image. Okay, so this actually, so good job here too. This is an LROC image actually. The sun angle though is really high. It's like almost straight overhead, which is horrible for trying to look at features on the surface. Craters that, huh?
When we were studying this, he's like, I don't know how to put an arrow above it, but I think it's coming almost nearly above it.
Yeah.
So it was hard to put that arrow in.
Yeah, no, but you're right. Yeah, it's roughly coming from that direction, but just pretty much overhead. So unfortunately, that can really mess with how you see things. Those craters in some ways look not circular, but in reality they are. So anyway, so this is an LROC image, just a really bad sun angle for looking at things. So go ahead and go on. Yeah, it's a much better picture that you've got there. Where was it? Maybe it's in the next picture.
Did you want me to move forward?
Go to the next slide. Okay, it must be, yeah, and then go to the next one with the text.
Oh, the text.
there was something that caught my eye. Maybe it's okay. Go ahead and go back up to the picture. Okay, real quickly, just do a little ranking exercise here in terms of relative ages between the mare and the highlands, the mountains, the highlands. Hadley Rill and Hadley Crater, the bigger crater. Rank those from oldest to youngest for me.
Well, the crater's the youngest.
Then I think it would go Rill and then mountains and then Mar.
Why do you guys say the mountains before the Mar?
Well, because the mountains had to be on something, wouldn't they? Would they be on the Mar? Because it looks like they impacted the Mar and then built up.
Okay.
Because I would think
Wait,
they
wait,
were
wait.
flat.
But the Mar was formed from the basalt flows that came to the surface, and the mountains would provide a perfect edge for them to butt up against.
That's true.
Like a
So
big cauldron.
mountains are the oldest, crater's the youngest, and then the Rill's the
Second youngest.
mountains as the oldest, then the Mar, then the Rill, then the crater.
Okay,
That's
very
our
good.
final answer.
And I like the way you guys discussed it.
Yeah,
Okay, we worked it out. That's good. Okay.
yeah, yes, that's correct. Your second choice, yes, yes. So remember, highlands are the oldest features on the moon. That was the original crust.
Okay.
Always, 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 always. So yeah, so good job. Yeah. Okay. And that actually was the question, because I thought I saw some text somewhere where you said that the Mare was the oldest, and that's what caught my eye. Yeah, I love this picture because there's so much geology. It's so complex. Represents everything you can see on the moon. There's an Apollo landing site relatively near there. I really like this picture.
That's why we split it up, so we could get all the little details and things better.
Yeah.
Yeah. And this picture is actually from the 1960s. This is from one of the original lunar orbiter spacecraft. So in some ways, those images from that mission are actually higher resolution than even some things from LRO, which is quite fascinating.
Yeah, I like.
Yeah, this is a great picture.
Yeah, it's one of my favorites. The other thing I also love about Apollo 15 is if you can look it up on, unless you've already seen it, but go on YouTube and look up Apollo 15 hammer and feather experiment. Have you seen this?
I don't think so.
So the astronauts that landed on the surface for Apollo 15, they took with them, well, they had a hammer, of course, had the rock hammers, but they also took a feather, a falcon feather with them, because that was the name of their lander, was the Falcon. And they
Wait, which
record,
video?
sorry?
Sorry. You said which video for Apollo 15?
Hammer and feather.
Hammer and
experiment.
feather.
Yeah, and what they do, what Dave Scott shows is like they're testing Galileo, or Galileo said that in a vacuum, everything falls at the same rate, right?
Oh,
So he drops the hammer and the feather at the same time, and they hit the ground at the same time because there's no air resistance to slow down the feather. So if you were to try that, if you were to try it on Earth, it wouldn't work. Yeah, it's a pretty quick video.
Yeah.
It's not real long.
Yeah, this is a little bit of a thing. So I did something like this in my physics class. The teacher, she had like her purse and she held it at her shoulder, and then she had it, one of the other students held something also at their shoulder, and they hit the thing. They hit the ground at the same time. So that was interesting because it was two different mass objects from two different heights, and she just kind of explained that they had different accelerations. Does that make sense? That's just what that reminded me of.
Well, the acceleration is the same, right? Gravity.
Because it takes more. Yeah.
One has
One has more
more.
inertia.
Yeah, it turns out to be a ratio between the two, the distance of the object. But yeah, gravity's gravity pulling at the same
Yeah.
acceleration. But the one takes longer to gain a little bit of speed too.
Mm-hmm.
Anyway,
Interesting.
so yeah, that's a cool video. It's another thing I like about Apollo 15. not that he has anything to do with this, but Dave Scott is one of the last remaining Apollo astronauts to have walked on the moon. There's only a couple, like 2 or 3 of them left. So they're a dying breeds, no pun intended. Okay, very good. All right, let's go on to your asteroid slides.
Yeah, where is it at? Okay, and then once again, I'm Jalen, and that's Asher. You
Hello.
can't see us now, but this is our Asteroid 101 presentation. And the first image that we have is Itokawa, and this is like a peanut-shaped asteroid that measures about 330 meters in diameter with a mass of about 35 billion kilograms. It's most known as a rubble pile because it's made up of several boulders, just ranging in sizes. And there's a theory that it was actually made up of a few asteroids. The smaller asteroid labeled here was said to slam into the day, connected and stayed together, and has steep. I couldn't point them all out, and this was actually a wordplay for the name, so I thought that was pretty cool. And you can see the light is coming in from the left. And typically the rubble and the rocks and the boulders that attach this had higher albedos than, say, the Muses C. And then here we kind of have a description of that with some more facts, just saying it was the most common type of asteroid in the inner belt, and that it contains several unseen impact craters. They just became buried in the rubble.
And then we have Vesta, which is the second largest asteroid in our asteroid belt with a diameter of 525 kilometers. It consists of about 9% of the total mass of the asteroid belt, and it's only second in size to Ceres. It has a very, very high albedo, being the brightest asteroid in our solar system. The large impact craters, known as the snowman craters, pointed out right here, they do have names. The largest and youngest being Marcia, the middle one being Calpurnia, and the oldest being Minucia. It appears to be, I feel like it could be some kind of skipped impact or something that broke up and then hit in 3 separate places. The ridges on Vesta were formed during the formation of Vesta, as it was still a molten mass, and they also have names. The ones that I have found are Dilvia, Havilah, and Domna, and the ridges appear to be the oldest feature on Vesta because all the craters cross-cut over them, no matter how old or young they appear. Unseen on the north and south pole of Vesta, there are craters on Vesta, and they took out a large chunk of the south, creating a large peak in the middle that is, I think, about 28 kilometers high. Since Vesta has a very high albedo, all the darker albedo areas of Vesta are deposited materials from other impacts that have hit them. And an interesting thing about Vesta is, due to its largest size, it did get separated into a core, a mantle, and a crust. Its core being mostly nickel and iron, and then the mantle and crust separating out into lighter and denser materials. And then,
and the next, sorry, that was just our page of some information and some facts about Vesta. And next up we have Eros.
So Eros is a very small asteroid with about 33 by 13 by 13 kilometers. It is a S-type asteroid with, again, it's considered a near Earth asteroid, and it was the first to be orbited and have pictures taken of it from a satellite. The image shown has a lot of Eros is made entirely of regolith, which is just a lot of broken up rocks. And regolith can range from small gravel to dust, which is what the smoother areas of this image are, to larger humongous rocks that are, again, pointed out in this image. The light is, again, coming in from the right side of the image, with the dramatic shadows coming off of the boulders. Most of the asteroid is made of silicon and iron. That includes all the large rocks and everything. And on the next slide here, you can see a lot of very interesting coloring of the regolith. The darker colors are due to the solar winds being exposed and turning and changing colors, and the lighter colors are ones that haven't been exposed as much for different reasons, whether they've shifted over time and come to the surface recently, or just that's a spot where the solar wind doesn't hit as much, whatever it is. Eros is not large enough to be separated as a homogeneous asteroid. I mean, it's just basically solid all the way through, no like denser and lighter materials in the core. And then we got
here's our sites.
We're excited.
And some more we're excited and some more excited.
Yep. And that concludes the presentation.
Okay, well done again. Yeah, asteroids are interesting because there's just such a variety of them. So I'm glad you brought up at the last slide you were talking about like the lighter and darker regolith. Did they? I don't remember in the rings. Did they use excuse me. Did they use a word to talk about whether or not how long something has been exposed to sunlight? What they call that process? I mean, other than weathering.
I don't recall there being a specific word. No.
Besides weathering. That's
Okay.
the only word that I've heard for it. Yeah. Did
Okay.
you know of one, or are you just asking?
There is. It's called mature. You'll hear it a lot with the moon about how mature the regolith is, which has to do with how long it's been exposed to the solar wind. Yeah.
Yeah, they always say mature soil on Earth. You know, like that's a mature soil.
Yeah. So actually, that's another question. What's the difference between regolith and soil? You wouldn't have read about this, but I'm just going to ask you.
I don't know.
I'm not too sure, but my best guess is that regolith has a different composition than soil, and it's gonna be created in a different way than soil was.
Okay. Yes and no. Yes and no. So it has a different composition in a sense that soil infers that there are organics are present. So
And then
regolith is simply just broken down rock. And you can have broken down rock on Earth. I mean, that just happens from weathering processes. But as far as we know, there's nowhere else in the solar system you're going to find organic material mixed within it to call it soil. Having said that, you will hear Mars scientists refer to regolith on Mars as soil. I think a lot of that has to do with it's just easier to say.
So it's kind of
So what?
Yeah.
yeah. I was saying so it's kind of just created from the deposits of the different impacts and stuff. Like impacts of the geological features. Could you say that?
Yes, so regolith is simply just rock that's being broken down. It's bedrock that's been broken down by whatever process, whether it's impacts, which is most common in a solar system. tectonics, if you have like an earthquake or a moonquake or whatever, that can jar a boulder loose and send it rolling down and break it up. There's all kinds of ways you can do it. The question technically, the technical difference is soil assumes there's some kind of organic material mixed within it. Anyway, just one of those little asides.